Rajesh sir, uh, Rajesh sir,
Yes,
I
sir.
am audible, sir. Sir, please start the sessions.
Okay, shall I start then? Okay.
Yes, yes, yes.
Okay. Okay. Very good afternoon to everyone. Myself, Rajashri Chakraborty, Assistant Professor, Department of Mechanical Engineering from GKCM College, as well as I am the joint co-convener of this event. A very warm welcome to all of you. Our third day of this FDP. Today we have our honorable guest and speaker, Professor Dr. Sunipa Roy, Madam. Before we start our session by Sunipa Ma'am, I would like to give some small introduction about Ma'am. We are very much privileged and honored having Dr. Sunipa Roy, Madam. Madam Sunipa Madam received her PhD degree from Jadavpur University in Electronics and Telecommunication Engineering Department in 2024. She is presently serving as Associate Professor and Head of the Department in Electronics and Communication Engineering at Guru Nanak Institute of Technology, Kolkata. She is the recipient of National Scholarship from Government of India, Junior Research Fellowship from DST, Government of India, and Senior Research Fellowship direct from CSIR, Government of India. Her current research interest includes nano device, graphene, supercapacitor, and gas sensor. She has more than 40 publications in high impact factor journal and CPD credited conference publications. She is the author of 3 books of international publishers like CRC Press, Bentham Science, and owns several book chapters of internationally reputed publisher. Dr. Roy is the senior member of IEEE, Secretary IEEE CASS Kolkata section, and published several patents. She is also the regular reviewer of IEEE transaction on nanotechnology and many journal of repute. She has been invited as an invited speaker in several national and international programs and chaired the session of many sponsored international conferences. Dr. Roy is the principal investigator of several funded projects and supervising many doctoral theses at this moment. So we are very much delighted to have Madam. Once again, we must say this, and we are handing over the session, Dr. Sunipa Roy, Madam. Madam, you can start. Madam,
Thank
are you
you,
ready?
everybody.
Yes, ma'am. Yes,
Thank
ma'am.
you,
Thank you, ma'am.
everybody. Okay, Principal Madam, Rajashri sir, and all the organizing committee members for providing me the opportunity to present my research in front of you. I'm sharing my slide. I hope it is visible.
Yes, ma'am.
Yes, ma'am. Yes.
So today my topic is particularly gas sensor, that is graphene based. How it work on how graphene works on sensor environment and why people are choosing graphene, because there are so many semiconductor material and so many gas sensing material is there. Still, we are inclined to graphene nowadays, and the total research has been shifted to search that find the advantages of graphene. So to start with, fabrication of sensor is not so easy. Fabrication of sensor is not so easy. So to start with graphene-based sensor, we should know how the sensor works actually, because all of you are not belong from the similar field, and maybe you are not having any idea how gas sensor works. So I am starting with that first. So I have so many slides. Actually, I have ready slides, and I am not actually not cut and paste all these things. I'm not doing. So I may skip the slide that is not feasible to you or beyond of the scope of this topic. So first is there are so many deaths in the coal mines in India due to the presence of methane. and approximately 50 numbers of methane sensors are needed per coal mine. So overall sensor requirement in India is huge, but not that much technology, particularly foundry system is missing in India. So Government of India now going to develop some foundry system, that is the mission, National Semiconductor Mission, NSM. Government of India has taken the initiative, great initiative. So this type of sensor, all this manufacturing could be possible in India within few years. So as we need lots of sensors, so while fabricating sensors, we should know what are the limitations, what are the matters we should look for. First one is temperature, operating temperature. Second one is power consumption. So power consumption, not only for sensor, everywhere in our household also, we always seek for power consumption because we check that whether it work on low power or low wattage is there or not. So low power dissipation is the prime criteria while we are selecting the gas sensor. And also there shouldn't be high operating temperature, because if the operating temperature is high, then battery will consume very fast. So that should be avoided. So large power dissipation can be considered greater than 1 watt, and high operating temperature can be considered as greater than 300 degrees Celsius. So low power device means at least less than 100 milliwatt we can consider as a low power device. That is not particularly MOSFET, because MOSFET, etc., is the power consumption is very, very less. It is less than 1 milliwatt even. But for this type of device fabrication, we will consider only less than 100 milliwatt power consumption. So you should keep in mind that we need operating temperature, not high for this gas sensor material, gas sensor. It should be at least 100 degrees centigrade temperature, less than 100 degree or less than equals to 100 degrees centigrade temperature would be considered in this nanotechnology domain. So these 100 degrees Celsius temperature, who will generate this temperature, how we can get this temperature in a particular device, that is the point of question. Because when you are handling a device, that is obviously battery operated. So there may be a 9-volt battery, 2 9-volt battery. So if the power consumption is huge, then, and if you have to go to the for the field work, say you are carrying the device, carrying the instrument, and this 9-volt battery could consume in 2 days. That is not possible. So this sensor, this gas sensor particularly, we carry in coal mines, etc., in many hazardous area, that is remote area. So it is not possible to carry chunk of battery in our packet and go with that sensor material. It is not possible. So we should keep in mind, we have to develop a low power consumption device. So this is less than 100 degrees Celsius. So who will generate this temperature? We will discuss later. So to circumvent this type of problem, the sensing temperature, to reduce the sensing temperature, first and foremost thing is we have to shift to thin film. What is the difference between thin film and bulk material? Bulk material, say you are taking graphite. Graphite, if we exfoliate it or if we cut the layer one by one, you will get graphene. So graphite is the mother, graphene is the child. So the thing is that when you consider a bulk material and we consider a thin film of same material, the characteristics are totally different. The electronic properties, optical properties, mechanical properties, etc., totally different, though the mother and child belong from the same category. This is the characteristics of thin film. So we have shifted to nanocrystalline material. So that nanocrystalline material is very miniaturized structure in the order of nano domain, 10 to the power -9. and the power consumption is very, very less. And we are also using to reduce the power consumption of the device that is less than 100 milliwatt. We should move to the MEMS technology. So what is MEMS? I'm going through. And this low temperature requirement, we have to build micro heater. So heater, we are comfortable with heater in our household. Many of us keep heater in our kitchen. But micro heater and heater, the difference between that in our household, the heater we are using, that is a very, very long wire and it is twisted. But in micro heater, the length of the wire is of the order of micron and the thickness of the wire is of the order of microns, like 50 micron only, 20 micron, thickness of the wire. And the length of the wire is roughly 1000 micron. So this is very difficult task to fabricate the micro heater, and for that we have to follow so many processes. If we don't follow the processes, we will not be able to develop flawless micro heater structure. It will cut, otherwise it will be broken and it will not generate the temperature, because broken micro heater means there is no continuous conduction. So micro crack, this is called, this broken I am telling, but technically we call it micro crack generation. This micro crack generation is very, very prone to, because the sensor we are keeping not at home, not in Almira or not in a safe place. The sensor we are putting it in hazardous area, open to environment, in some coal mines, and where dust, pollen, etc., rainwater, everything is there. So this micro heat, obviously my heat, that is sunlight, everything is there. We put the sensor in that place to sense the hazardous gases. So the thing is that we have to make it rugged, and we have to try that micro crack generation could be avoided. So now the thing is that first we move through the microelectronics fabrication part. Let us start with the MEMS technology. What is MEMS? MEMS is nothing but the microelectromechanical system. So the name suggests that it's mechanical system. So mechanical means there is a concept in our mind. Mechanical means something is moving, something is rotating. But always that is not true. This MEMS technology we are implementing in the sensor, in fabricating the sensor, that is not using any movable material, movable parts. The thing is that the technology that is used to fabricate MEMS, the same technology we are using to fabricate our sensors. That is, this is called MEMS-based sensor. So this is particularly MEMS. MEMS is totally depends on micro machining. Micro machining, this is an example of micro gear or micro gear, this picture I am showing you. You can see how the structure has been formed. This is obviously of the order of micron level. And this structure, the one and only way or method that we can adopt to fabricate this structure is micro machining. So next, I am skipping some slides. So the target of our MEMS is response time of the sensor is very small. The miniaturized device, very, very small device can be fabricated, higher sensitivity, reduce thermal mass of the device for this using this MEMS technology, and power consumption can be scaled down. So again, I am telling 3 key points. That is small size of the device, batch processing using VLSI technology. That is, batch processing means at a time, if we need hundreds of sensors, we don't have to wait 100 times fabrication process. We have to go through 100 times fabrication process. Take a silicon wafer and make 100 sensors at a single time, same time. So this is the point. This is called batch processing. Integrability, that means sensor and the signal conditioning unit could be integrated on the same chip. That is one of the greatest advantages. So here you can see the MCQ, but this MCQ could be shared by the organizing committee also. I am skipping this slide. So now the silicon, this MEMS technology, now the term you should be familiar with it, that is CMOS compatible. What is CMOS compatible? CMOS compatible means the device is fabricated on silicon. So why silicon? Because silicon is very inexpensive material. Silicon could be fabricated, prepared from sand. Sand is raw material that is available in the nature. It's free of cost. So we don't need to purchase the raw material, at least from the third-party vendor. So that is the thing. It is available in the abundant in the nature. We can take silicon, process it, and fabricate the silicon wafer. We can take sand, process it, and fabricate the silicon wafer. So silicon, obviously very good material. This is a little bit brittle, but hardness, Young's modulus is very, very high. So next is, I have mentioned that batch processing. So this is one of the example of batch processing. See, sorry, I have to. So this is the batch processing technique. See, using a single wafer, how many devices can be fabricated? So this is the silicon ingot, silicon wafer. After cutting this ingot, we are getting silicon wafer. That is roughly 300 micron thick silicon wafer, and the thickness is 2.5 inch roughly. It may vary, but generally we take this sized silicon wafer, and the method we follow to fabricate the silicon wafer, that is Zoralski method. So the total, this is called ingot. The right hand side part that we can see, that is ingot, and that is totally this one, that is ingot, and that is totally fabricated from sand. There are some process obviously involved with it, but the raw material is sand. Now, so first thing is, after having the silicon wafer, you know silicon is the semiconductor. It is not conductor, it is not insulator. Semiconductor at room temperature. But if you increase the temperature of the silicon, one time reach, it will behave like the conductor. So what will happen if the temperature of the silicon wafer will rise? And on top of silicon wafer, obviously you are going to fabricate some device. So if the temperature of the silicon wafer raised, what will happen? This will become conductor, and the device that is fabricated on top of silicon wafer, that silicon and the device will get shorted. Short circuit will be there. So it will damage the whole device. So for that reason, we have to deposit silicon dioxide on top of silicon wafer. What is silicon dioxide? Silicon dioxide is nothing but a very good insulator. There are so many good insulators available in the market that is silicon nitride is much better insulator than silicon dioxide, but still research is inclined with silicon dioxide dielectric. Why? Because silicon dioxide is very easy to deposit, whereas silicon nitride fabrication is high-end laboratory is required, and it is not so easy task. So research is inclined on the silicon dioxide dielectric. So take the silicon, on top of that silicon dioxide layer, you please deposit. So there are two types of oxidation process. First one is dry oxidation, another one is wet oxidation. Dry oxidation means, as the name suggests, there are no water molecules involved. For wet oxidation, as the name suggests, some water molecules are involved. For dry oxidation, we are using just silicon and oxygen. That is enough for dry oxidation. But for wet oxidation, we are using silicon, oxygen. With that, we are, carrying, we are inputting some water vapor inside the chamber. oxidation furnace. So you see, as the number of oxygen molecules are more in wet oxidation process, because we are water molecules are getting added with it. So that is the thing. Wet oxidation is much faster than the dry oxidation, as the number of oxygen molecules are more. So why people are still working with dry oxidation process? The thing is that in dry oxidation, the surface finish is smooth, but it takes longer time. Whereas for wet oxidation, surface finish is not that type of smooth that is observed in dry oxidation, but the process is faster. When we have to fabricate the device, we have some deadline, we have to fabricate the device within some deadline, don't have much time, then we should go through wet oxidation. And wet oxidation, obviously, there is a compromise. Whether we choose dry oxidation or wet oxidation, it depends on the requirement totally. So these are the few fabrication steps, that is cleaning, deposition, etching, and patterning. So first we go through cleaning, because device cleaning is not so easy task. So why cleaning is required? Because there are so many contaminants available in the weather, in the atmosphere, in the ambience. So what are these type of contaminants? Dust particle. The micron level dust particles are present in the air, what we cannot see with naked eye. So there are so many oil and grease are present. We can't see naked eye. So these type of contaminants are always present in the air. So method of cleaning, if we follow, there are two types of cleaning, like oxidation, that is wet cleaning, and dry cleaning. Wet cleaning, obviously, we using water, and for dry cleaning, we are not using water. So dry cleaning, for that dry cleaning, we need a big setup where the cleaning, the external foreign particle that is attached with the silicon wafer could be removed from the wafer surface. That is the part of the dry cleaning. And wet cleaning is the wet process, where we are using water. So what are the difference between wet cleaning and dry cleaning? When people choose wet, when people choose dry? So dry cleaning, high-end laboratory is required. There is a financial constraints. Those who are capable to establish the setup, well and good. But wet cleaning is less expensive process. Wet cleaning is less expensive process. In our laboratory also, we can do this wet cleaning process very easily. So it depends on the requirement and also some conditions. So wet cleaning means you can take sulfuric acid, you can take hydrochloric acid, etc., with some added water and with hydrogen peroxide. It is using actually as a buffer solution. If we use hydrogen peroxide, buffer solution. Buffer solution, what is the function of buffer solution? Buffer slow the process. The process getting slower when we use some buffer solution due to some chemical reaction. So the thing is that, so there are some metallic impurities, so many calcium, cobalt, copper are present. There are so many slides on cleaning method. So this is the summary, because this is not beyond of our scope to present all the detailed study in this lecture. So if you carry the silicon wafer and put in trichloroethylene, first boil and then put 3 minutes in ultrasonic cleaner, it will remove the organic compounds and also dust particle. And step 2, if you put the silicon wafer into the acetone, it will remove oil and grease. Step 3, if you take the silicon wafer and put in the sulfuric acid, it will remove the sample clean in DI water, and to remove inorganic compounds from the wafer surface, we use ammonium hydroxide. And to remove hydrochloric acid from the sample, we use some, to remove the alkaline organic compounds from the wafer surface, we are using hydrochloric acid. So these are the summary. Now the thing is that this is very interesting. What is clean room? Because while the microelectronics fabrication is being carried out in the clean room. So what is clean room? A clean room is a controlled environment where pollutants like dust, airborne microbes are filtered out in order to provide the cleanest area possible. So this is the class of clean room. I mean class 1, class 10, class 100, class 1000, class 10,000, class 1 lakh. What is that? It is written over there at the bottom of the table. See, a class 100 clean room, for example, would not contain more than 100 particles bigger than 0.5 micron in a cubic foot of air. So 0.5 micron foreign particle should not be there in number of 100, more than 100 in a, if we call it class 100 clean room. And the area, volume of the air is 1 cubic foot of air. So class 1 clean room means one particle bigger than 0.5 micron should not be present in the 1 cubic foot of air. So hope you understand, or hope you assimilate that class 1 clean room maintenance is very, very costlier process rather than class 10,000 or class 1,000. Because once you the setup of clean room is complete, that is not the end. You have to maintain the clean room. So for the maintenance of this clean room, what should we do? There are so many HEPA filter. It's a high efficiency particulate air filter, ultra low particulate air filter. You have to incorporate inside the clean room, and outside air is first circulated to a filter system. So this is the picture of the clean room I have collected from the web. And the particle counter we need to maintain the clean room. There are so many devices we need to maintain the clean room. What is the particle counter? The formula is NL equals to root over A. NL is the number of particle measuring points, and A is the area of the clean room in square meters. I mean, clean room, the area say 100 square meter if the area of a clean room. Then number of points where you have to measure checkpoint. Point means checkpoint. Number of checkpoints you should measure the clean room, whether it is maintained or not, that is equals to 10. Root over of 100 equals to 10. I mean, in a 100 square meter room, you have the checkpoint should be 10 for the maintenance of clean room. So this is the particle counter, that is one is handheld and another is bulk. So all these are present in the market, available in the market. So there are so many things, not only particle, humidity, pressure, temperature, all should be maintained to the point in a clean room. For that, we need different types of devices to maintain the clean room process. This is very costlier process, that is in India particularly, this type of clean room is not available. Now I am ignoring the MCQ, organizer will provide you. So silicon micromachining. There are two types of micromachining. First one is bulk micromachining. Second one is surface micromachining. So bulk micromachining and surface micromachining, one is called subtractive process, another one is called additive process. So just a minute. Micromachining. Okay. Is there any question, madam? Also, the upper figure is the example of silicon micromachining, bulk micromachining, and the lower figure is the example of surface micromachining. Here we can see why this is called subtractive process. The gray colored material is nothing but silicon, and through bulk micromachining technology, we are removing the silicon from the bulk counterparts. So as we are subtracting silicon from the bulk silicon wafer, that's why this is called subtractive process. Whereas surface micromachining called additive process, because we are taking silicon substrate, we deposit the, anything SiO2 layer or any photoresist layer, say this is SiO2 layer. Then on top of that, a polysilicon layer or any metallic layer, maybe gold, maybe platinum, any metallic layer can be deposited. And if you put the wafer into the hydrofluoric acid is good etchant of silicon dioxide. Silicon dioxide will be etched out, and the resultant structure you will get this one. This one will be your resultant structure. As we have started with silicon wafer, we are ending with this additional structure. That's why this is called additive process. Sorry, yes, this additive process. Now, please, I'm moving to the next slide. So if we go for etching, wet chemical etching and dry etching, generally bulk micromachining is done through wet chemical etching. This is very easy process, wet chemical etching. See, just take a beaker, take some solution that is maybe acidic or maybe alkaline or acidic, any type of solution you can take, and put the silicon wafer. Depending on the requirement, the silicon will be etched out. So requirement of the temperature, there is some temperature needed and silicon will be etched out. So that is the bulk micromachining. Obviously, when you are opening this window, this is one window. When you are opening this window actually I am telling about. This window opening, for this window opening, we have to do the photolithography process. We have to follow the photolithography process prior to bulk micromachining process starts. So that is the thing we should maintain in the technology, fabrication technology, microelectronics fabrication technology. So next we are moving to wet chemical etching. Wet chemical etching, two types. One is isotropic etching, another one is anisotropic etching. Anisotropic etching, always some angle is there, maybe 90 degree, maybe 60 degree, maybe 50 degree, right? Here we can see anisotropic etching, the lower one, that is 90 degree steeper structure we have achieved. But the upper one is called anisotropic etching, where, isotropic etching, where we can see the round type of structure, round shape structure. Isotropic etching, not direction dependent, but an isotropic etching is direction dependent. Particularly when we follow dry etching do the anisotropic etching. But wet etching, wet chemical etching, we can get anisotropic as well as isotropic etching, both. So moving to the next slide. This is the actually structure that is you can see here, anisotropic etching and isotropic etching, and also a three-dimensional picture I have put for better understanding. That is, you can see the V groove. This is called V groove. This is called V groove, and this is called U groove. So V groove and E groove is nothing but if U groove could be extended. If you extend the time, it could be turned into V groove. So V groove and U groove depend all on the requirement, that is how much window you are opening. This is the window actually you are opening. This is the starting window. This is called starting window, and this is the resultant window. The window you are opening, it depends on, depending on that, we can understand that whether we will get V groove or we will get U groove. And the thing is that this is a natural process, that if you start with 100 silicon wafer and you will get 54.7-degree angle in the silicon wafer. Okay. If you start with 100 silicon wafer. 100 silicon wafer means that is Miller indices I am telling about, that is HKL. That is H is nothing but 1 by X, K is nothing but 1 by Y, and L is nothing but 1 by Z. So number of atoms present in X-axis, number of atoms present in Y-axis, number of atoms present in Z-axis. Obviously, silicon atoms I am talking about. So HKL 100, that means there is no silicon atom present in Y-axis, no silicon atom present in Z-axis. Only silicon atoms are present in the X-axis. So 100 type of silicon wafer is called loosely packed. That means number of silicon atoms are less. But if you consider 111 silicon wafer, that means HKL111, that means X-axis, Y-axis, and Z-axis, all are clubbed with the silicon wafer. So this is densely packed. So obviously etching process will be faster if you take some loosely packed silicon wafer, silicon atom, because the etchant can penetrate easily inside the silicon wafer because there are enough space. But if you consider 111 silicon wafer, there is not enough space. So etchant cannot penetrate easily inside the silicon wafer. So if you need faster process of etching, you should take 100 silicon wafer. But if you need a very steeper structure, very accurate structure, then you should go for 111 silicon wafer. So all depends on the requirement and research, based on research actually. So this is the schematic I have put, that is one for pressure sensor, one from gas sensor. That is all are bulk micromachined silicon, and everywhere we can we use this micromachined device, maybe pressure sensor, maybe gas sensor, and many more places also. In IoT, we are using so many sensors, and there are huge application of MEMS technology. So I have already told that what is surface micromachining, but the thing is that surface micromachining is an additive process. I have already mentioned this, that how a cantilever has been fabricated on top of silicon wafer. And one more thing you should learn, that is sacrificial layer. Whatever the material we have deposited, maybe silicon, maybe other else, that is actually dissolving into the etchant, I mean hydrofluoric acid for silicon. So this oxide layer is getting dissolved in the etchant because it is sacrificing itself to make the this micro cantilever. So that's why this is called a sacrificial layer. So there is a stiction problem in surface micromachining. That is, the gap between the micro cantilever and the silicon is very, very less. So if you wash it with water molecule or with any chemicals, if you wash it with any chemical, there is a problem of stiction. That means chemical molecules may get stuck between the structure and the silicon, and it is not so easy task to remove this molecule that is stuck from in between the two layers. It is not so easy tough to remove it. So there are some process, that is critical drying with CO2. That is the process we can remove the molecule inside the trap, from the trap. And also, if we could make the structure stiffer, then there we can avoid the stiction problem. So this is CMOS compatibility, that is CMOS fabricated. You can see particularly the people belong from EC background. This is the structure of CMOS, that is gate, drain, source. You can see easily, and on the same chip, I mean, on the same silicon wafer, the MEMS device has been fabricated. That is one sensor has been fabricated. So this is the example that we can, I mean, integrate the MEMS with CMOS. That is one of the greatest advantage of CMOS technology or MEMS technology. So another MCQ. So this is a clear picture of bulk micromachining. This is your starting window, that is WO. WO is the starting window. This is the starting window. This one WO, and this is your resultant window. So this is the formula. By applying this formula, we have to calculate how much will be the opening window or the starting window. So WB equals to WO minus 2L cot 54.7 degree. So WB we can calculate in this using this formula, and L is the depth of the bulk micromachine. How much length we will etch out? It will be etched out. That is nothing but the L. And this 54.7 degree is inherited, that is natural process. If you start with 100 silicon wafer, it will obviously etch out with 54.7 degree. No human intervention is there. It is a natural process. So by this way, we can calculate our resultant window. So next is so this is the steeper structure. So I'm not going much deeper. So isotropic etching, I have already mentioned. Choice of etchant is a good factor. What type of etchant should we choose? This is the difference between wet etching, dry etching. First and foremost is dry etching more expensive, wet etching less expensive. And the next process is optical lithography. Lithography process is a very, lengthy process. It takes much time to go through this lithographic process. Before starting the lithography, we should pre-bake the wafer. Pre-bake means just take the wafer, coat it with photoresist. Photoresist is nothing but the carbon polymer compound of carbon, and it is carbon polymerization is there. If you put the photoresist into the oven, this is at roughly 100 degrees centigrade or 200 degrees centigrade. It is called pre-bake. After pre-bake, you have to go through the photolithography process. Photolithography process, it is not so easy to understand if you go through this slide. Still, I am trying to make it easier so that you can understand. That is the gray colored portion is the substrate. On top of that red color portion is the photoresist. And on top of that, this is nothing but this is nothing but the mask. This mask you have to prepare through software, and then you have to collect it from the vendor. And this is obviously just a tensile mask. This is plastic type of material. And see the portion that is blocked, it cannot pass the UV ray. The portion that is open, UV ray can pass through it, and it will soften the photoresist material. And after that, we are getting this one. That is, if we develop this wafer, and if this is positive photoresist, then if we develop, we will get the softened part will dissolved. We will get only hardened part. And if we get negative photoresist, I mean, if we are using negative photoresist, the thing is that in negative photoresist, the exposed portion gets hardened. The difference, this is just replica of the positive photoresist. In positive photoresist, the exposed portion, the portion that is exposed to UV ray, it is getting softened. And when we are using negative photoresist, the exposed portion is getting hardened. So if you put the silicon wafer after this exposure into the developer solution, then the softened portion will get dissolved and we will get this structure. So this is in this way we can have the structure on top of silicon wafer. This is just an example, and photolithography is called the pattern transfer mechanism. The pattern we want to transfer on the silicon wafer, that can be done only using photolithography. So next is, so UV ray exposure, it is shown. Photo mask is there. This is the example of photo mask. So after photolithography is over, you have to clean the wafer and put inside the oven. This is called hard bake. First one is pre-bake, and this is called post-bake. First one is called pre-bake or soft bake. Last one is called post-bake or hard bake. Because why this post-baking is required? Because after developing, there are so many unwanted material, unwanted chemicals might be present on top of silicon wafer that could be removed through this heating. Post-bake is nothing but the heating that could be removed through this heating process, and the chemicals will be waved off. So basically, these two terms is very important. One is HVAC, another one is lift-off. The difference between HVAC and lift-off is HVAC is take the silicon wafer, put the silicon dioxide that is green in color, right, light greenish, and on top of that you put and pattern the photoresist. And if you third step, that is, if you put it into the hydrofluoric acid, the silicon dioxide layer will be dissolved. And now if you put the step 3 silicon wafer inside the acetone solution, acetone is a good agent of photoresist, then photoresist will get dissolved. So finally we get the structure that is mentioned in step 4. So this is called HVAC. Now the lift-off process. Lift-off process, just the replica of HVAC. First take the silicon wafer and coat and pattern the photoresist. Then deposit the silicon dioxide layer. And then you put the level 2, I mean step 2 silicon wafer into the HF solution. Not HF solution, in the acetone solution. Acetone is the good agent of photoresist. You can see that it will etch photoresist, and when photoresist will be etched, it will goes off by taking the silicon dioxide layer also, that is green in color. And finally, you are getting the step 4 structure. So if we go to the previous slide, see the HVAC and the next slide, lift-off, is just replica of the structure. So it depends on the requirement. Researcher could understand whether they should go through lift-off process or through HVAC process. So there are so many methods involved with I have shown you the optical photolithography. Not only that, there are so many other photolithography process also, but generally mostly used photolithography process is optical lithography. So this is the LIGA. LIGA means X-ray lithography, electroplating, and molding. This is the LIGA structure. What is LIGA structure? LIGA structure is high aspect ratio structure. When we are fabricating high aspect ratio structure, then we should go through LIGA process. This is the high aspect ratio structure. You could see the height is much more than the diameter. So this is called LIGA structure, and the process LIGA we follow to fabricate this high aspect ratio structure. Now our device is ready. Now we have to put it on a steady surface, because silicon substrate is very brittle. And if you put it elsewhere, their micro crack generation will be very, very easy, and it will damage the device. It will break the device. So all your effort will be in vain. So you have to place the silicon wafer onto the substrate, I mean stronger substrate. So for stronger substrate, we may take glass, because glass, take a piece of glass or glass slide, put the silicon wafer on top of that. It is not that type of easy process, because it should be bonded properly. The glass and the silicon, it should be bonded properly. For that, we should know what is Fusion bonding, what is anodic bonding? For fusion bonding, the process temperature is 1000 degrees centigrade. For anodic bonding, the process temperature is 430 degrees centigrade. For fusion bonding, we actually bond actually complex 3D structures. But when we are bonding the silicon structure on top of the glass substrate, we go for anodic bonding. So silicon to glass bonding is anodic bonding. Silicon to silicon bonding is nothing but we follow fusion bonding. So move to the next slide. You can see fusion bonding. See, two silicon wafer has been bonded. Wafers have been bonded. That is how? By this is mechanical process. The silicon wafer is made hydrophilic, not hydrophobic. It is made hydrophilic, and then apply the pressure, and huge pressure is required, and annealing, and then anneal at greater than 1000 degrees centigrade, and now the silicon will bond together. So this bond is nothing but called SiO-Si bond, because first the silicon wafer has been made hydrophilic. Some water molecules are present in between them. So SiO-Si bond is a strong bond. It will not break further. So this is the example of bulk micromachining, micromachined micropump. Here we can see 4 structures have been bonded through fusion bonding. Next is anodic bonding. We can see that the orange in color or yellow in color is the glass slide, and lower one is silicon. Lower one is silicon. This glass and silicon bonding, for that we need some potential, and this potential we need, and actually this electric field makes it possible to bond between glass and silicon. So the alkali ions actually Na+ ion move away from the interface, and in this way, after applying this potential, and now the silicon glass can be bonded. This is nothing but for the rugged structure. To make the structure rugged, we follow the silicon glass bonding through anodic bonding technology. There are some MCQ. Now next the part is thin film sensor. So this is the microfabrication. This is one process animation. You will we get much more familiar how the fabrication, microelectronic fabrications are going on. Cross-sectional view and top view. This is silicon wafer I have taken. This is silicon dioxide. This is purple in color. Purple in color that is not taken by me. That is not, it is as per my choice, because when you deposit or the silicon dioxide layer on top of silicon, then depending on the thickness of the silicon wafer, the color varies. Actually, when we are taking, say, roughly 0.5 micron thick silicon dioxide layer on top of silicon, then the color will be purple. If we take, say, 0.7 micron silicon dioxide layer on top of silicon, the color will be orange. Then if we take 0.3 micron silicon wafer on top of silicon dioxide layer on top of silicon wafer, then it would be greenish in color. So all depends on the light reflection, because thickness, this light reflection depends on the thickness of the silicon wafer, number of SiO2 silicon dioxide atoms present in the surface, all are surface phenomena. So after that, this is bulk micromachining. After that, the metallic layer deposited for pattern transfer through photolithography. This is some pattern has been transferred as we are dealing with gas sensor. This is microheater has been, this pattern has been transferred. Then some sensing layer has been deposited on top of the microheater structure. So this is the final structure we have got. This is the sensor structure. Now thin film, what is thin film? theoretically less than 1 micron is called thin film, but practically less than 1 micron will not serve the purpose. Actually, less than 1 micron, it is roughly less than 500 nanometer could be considered as 500 micron, sorry, less than 500, because 1 micron is 1000 micrometer. 1 micron is 1000 nanometer. 1 micron is 1 micrometer, that is 1000 nanometer. And that is less than 500 nanometer is called practically thin film. So what is thin film? Thin film enhances sensitivity, faster response, annealing temperature is lower, chemically stable. So this is the basic gas sensing mechanism. Due to the natural non-stoichiometry, if you take metal oxide, that is zinc oxide layer, and zinc oxide is not complete. There is a, this is inherited. That is God gifted. There is natural non-stoichiometry present in the metal oxide layer or any deposited material, chemical. This is metal oxide in my case, as we are dealing with gas sensors. So due to this natural non-stoichiometry, the ambience oxygen, that is oxygen present in the atmosphere, is getting absorbed on the surface, because zinc oxide oxygen molecule will try to complete itself by taking the oxygen from the atmosphere. So when oxygen is giving the, making the poor bond with the surface atoms of the sensing layer, oxygen is accepting the electrons from the gas sensor sensing layer surface. That's why it is becoming O-, and the sensing layer surface is becoming positive. So thus here we can see the poor bond has been established. This bond is called dangling bond. So actually sensing layer surface is the donor and the oxide layer, oxygen atom is the acceptor. So this is the donor-acceptor relation. So as sensing layer surface is donating the electrons, so less number of electron means resistance is more. That's why we are starting in next slide, we are starting with the high resistance. This is the resistance is higher. But when gas comes, target gas comes, hazardous gas, say for methane, then methane will make the bond with the absorbed oxygen and will make CO2 and H2O and goes off. When the oxygen goes off from the surface of the sensing layer, it will return back the electrons to the sensing layer. As the number of electrons now increased, that's why resistance has been decreased. So resistance is less in this case. So this is the basic characteristics of the gas sensor. So when we are considering resistance, when the resistance is less, the resistance, the gas is present, we can consider. When the resistance is higher, we can consider gas is absent. So this is the basic thing of gas sensor, basic characteristics of gas sensor. Now, here you can see, this is self-explanatory flash player, silicon, SiO2, then metal oxide, some absorbed oxygen is there. This is the red color one or orange color one is the target gas, hazardous gas. After, see here, after reacting with the absorbed oxygen with target gas, the electrons, free electrons will return back to the semiconductor metal oxide layer surface or sensing layer surface, and these all are the byproducts goes off from the surface, that is CO2 and H2. These all are the byproducts. So in this time, the sensor resistance will decrease. So this is one of the structure, and now I am moving to the graphene part, that is hope it is visible. Is it visible? The graphene slide?
Yes, ma'am. Yes, ma'am.
Okay, very good, very good. You know what are the function of gas sensor? That is, I am not going to already explain in earlier slide. The performance characteristics, sensitivity, selectivity, response time should be less, sensitivity should be higher, and small size, low power consumption, capability of being wireless. All these are the desired. We desire this type of sensor we should fabricate. So So why graphene? Graphene electrode is better choice for room temperature gas sensor. Earlier, we can see that we have used some metal oxide layer, we have fabricated the gas sensor device, but the problem is that we have to fabricate microheater. Why? Because who will generate the temperature for that gas sensor to activate the sensing layer? That's why we have fabricated the microheater. So the thing is that that sensor was not room temperature gas sensor. Room temperature means 27 degrees centigrade temperature. 27 degrees Celsius temperature, but that gas sensor was operated at 100 degrees Celsius temperature or 200 degrees Celsius temperature. So that temperature could be generated from microheater, but the system has been shifted to graphene. Why? Because this type of microheater, etc., we don't need to fabricate. The fabrication steps has been reduced. It is user friendly also. So if we can fabricate the graphene based room temperature gas sensor, it will be easy. So why graphene? Because we use graphene because of high carrier mobility, increased specific surface area, low intrinsic noise. Why low intrinsic noise? I don't know. Someone is uh, on mute, I think. Some noise is coming. So graphene, why?
Tuhin Shubro Das sir, kindly mute yourself. Okay, ma'am. Continue. Tuhin Shubro Das sir, please.
Flow of electron. No obstacle is there in the flow of electron. Graphene is such a material. That's why it has got low intrinsic noise. I mean, low obstruction means no scattering is there, no scattering loss. That's why this is low noise device. And pristine graphene, we can see that is the pure graphene is called pristine graphene. Graphene property, if we go to the next slide, then this is the graphene structure that is I'm not finding, I'm unable to find the slide. I don't know. So the thing is that, see what is happening. The conduction band, why we should avoid pristine graphene, pure graphene, that is conduction band and valence band in pure graphene touches each other in 6 places. That is called Dirac point. So for that reason, this pristine graphene is not a good match for gas sensor because we can't manipulate the forbidden energy gap between the valence band and conduction band because it is already touching each other at 6 different points. So that is the thing we should work with, not graphene rather than graphene oxide we should work with. Because if we add number of functional groups with graphene, it could be a graphene oxide and the distance between the forbidden energy gap that is the distance between the valence band and conduction band could be increased. So somewhere purity is not the blessing, is the curse that we can see in graphene. That is, impurity is the blessing for graphene when we use in gas sensor, because the forbidden energy gap that was not present in the pristine graphene could be introduced by using reduced graphene oxide. So now we can see the different amazing property of graphene material, that is electronic property, high electron mobility, room temperature is 2 lakh centimeters square per volt second, whereas silicon has 1400 centimeters square per volt second. Obviously, silicon 1400 mobility is when we are using p-type silicon. For n-type silicon, the mobility is 2500, 2500 centimeter square per volt second. But we prefer to work with p-type silicon in microfabrication process. Why? Why not silicon of n-type we take? The thing is that n-type silicon mean number of electrons are more. So there is a scattering mechanism. Scattering mechanism, one electron bombarded with another electron that is fallen in its path. And scattering means there is a scattering loss. So that is the thing. Scattering means it will generate huge noise. So we should go for p-type silicon, because p-type silicon hole mobility is much less, and the noise production is less in p-type silicon wafer. So this is the electron property is excellent in graphene. Optical property is also excellent. It is not absorbing the light. 97.7% light transmitted from graphene layer. You mind it that graphite and graphene, graphite, say 1000 layer of graphene is called graphite. But when we detach this graphene layer one by one, then up to 9 to 10 layer, we can call it graphene. When it exceeds 10 layer, presence of 10 layer, then we have to call it graphite, because when it is 15 layer of graphene is present, then the characteristics is similar to the bulk graphite. And up to 9 or 10 layer of graphene, the characteristics of graphene is totally different from the graphite. And this property is all we are discussing, that is only applicable when we take these 9 or 10 layers of graphene. I mean 9 or 10 layers of carbon atom. Then we call it graphene. So next is some sensor material could be fabricated. I can show you how easy to fabricate graphene-based sensor. So here you can see there are so many processes involved while fabricating the graphene, and chemical vapor deposition is there, electrochemical exfoliation is there. Electrochemical exfoliation is very easy process, easier process, and chemical vapor deposition is a little bit, highly expensive equipments are required. It is costlier process, and also some hazardous process also, because hazardous gases are produced as a byproduct, and some acetylene or methane, some carrier gas is required to fabricate the graphene layer through this process. But the thing is that the graphene layer we are getting through CVD process, that is very, very pure graphene layer. And this electrochemical exfoliation process, the functional oxygen functionalities, many oxygen functionalities are present in the in this graphene, when we are following this electrochemical exfoliation process of graphite. So here you can see the video, and how I will show you later how it is possible to fabricate graphene sitting in our table also by using the Scotch tape method. So so this is some of the example of electrochemical exfoliation. I am not going much deeper because this is available in the web also, the process. So thick film and thin film. That is 1 micrometer less than is called thin film, and above 1 micrometer is called thick film. So there are so many processes of depositing thick film, thin film, that is physical vapor deposition process and also chemical vapor deposition process. These are the technology we are using: physical vacuum evaporation, sputtering, molecular beam epitaxy while doing the following the physical vapor deposition, and chemical vapor deposition also APCVD, LPCVD. This type of, there are many types of chemical vapor deposition, but thermal CVD, that is thermal chemical vapor deposition process, this is the most inexpensive setup we require. Else all other is very highly expensive, all other setup. So I am not going much deeper. Physical vapor deposition is nothing but take the metal and put on a filament and heat the filament, and metal will be melted, and then it will be deposited onto the substrate, because there is a heat and metal is getting evaporated and it will be deposited onto the substrate. This is the basic fundamentals of physical vapor deposition. Now the thing is that chemical vapor deposition, there are so many issues involved, that is volatility, stability, reactivity, safety with this chemical vapor deposition process. Here we can see the, just a moment, chemical vapor deposition. Here we can see how the process is going on. That is, substrate is blue color is the substrate. On top of that, the solid material is deposited. In this case, as we are dealing with graphene, you may consider this as graphene layer on top of silicon or whatever the substrate material. Substrate material may be silicon and SiO2 also, combined substrate material. So this green and yellow, the layer, we can see that is the solid material, that is may be considered as graphene, or mono layer of carbon atom, multiple layer of carbon atom, because I have already told that up to 9 to 10 layer we can consider it as graphene, 9 to 10 layer of carbon atom. Then this red and violet, this all type of molecule is called precursor molecule. That means the precursor means that is the raw material, that is we are using methane here, say, to deposit the graphene layer. This methane is the raw material in this case. Now you can see how it is happening. The target gas is coming, it is getting deposited onto the substrate, and we can get the graphene layer. Next, again, it is this is step by step I have mentioned using 3, 4 slides. Step 1, this is step 1. This is step 2, how target gas, after dissociation, the carbon is being deposited and hydrogen is as a byproduct, it goes out from the chamber. This is nothing but the methane or acetylene that contains the carbon atom. That much gas is required that contains the carbon atom. And high temperature is required. That is, chamber temperature should be very, very high, nearly 1000 degrees centigrade or 800 degrees centigrade. It is getting deposited. All are surface phenomena. And after deposition, the resultant byproduct goes off. So here we can see some, here, this is the direct point. I was telling that 6 places carbon in graphene layer, that is valence band and conduction band touches each other. This is the case of pristine graphene. This is the enlarged view. Enlarged view, I can show you here. This is the case of pristine graphene. This is the case. This is pristine graphene. This should be avoided until and unless you increase the gap between the valence band and conduction band. You can manipulate the forbidden energy gap. That is the first and foremost criteria of gas sensor, because you have to manipulate the when gas is coming or gas is goes off from the chamber or from the environment, when resistance is decreased, and when the resistance is increased, that is only possible by modulating the forbidden energy gap. When in gas sensor characteristics, I have already shown you that when resistance is decreased, then the forbidden energy gap is less. When resistance is increased, then the forbidden energy gap will be more. In this way, you have to manipulate the forbidden energy gap. That is only possible when graphene is added with some functional nanomaterial. Here it is graphene oxide actually. So this is the case. You see, this is a simple graphene sensor structure. This is simple graphene sensor structure. This is called GFET, that is graphene FET. Just take silicon on top of SiO2, on top of that gold deposited, and two gold contact layer is connected with graphene, and that graphene is working as a channel. Because we know in field effect transistor, channel plays a crucial role. Channel length actually plays a crucial role. So here, this graphene layer acts as a channel. So in this way, we can easily fabricate GFET, graphene FET, and there is a lot of scope of research already done, and there is already future scope also present. Those who are interested to work with on GFET may start their research work. So these are the things. This is new method, and this is actually that thermal CVD setup. You need the source of carbon containing gases and one furnace, high temperature furnace. Just put the wafer on inside the furnace and flow the carbon containing gases, make it available inside the chamber. Carbon will be deposited onto the substrate, and the rest of the byproduct will go off. This is the thermal, the most simplest setup of graphene deposition. So next is some characterization process are there. This is beyond of the scope of this lecture. So stability study, when we are dealing with some sensor, stability study is very, very important issue, crucial issue, because someday you are getting good stability, someday you are not getting that much of resistance. That is not a good sensor. So if you hold it for 30 days in the same environment, and if the line is straight, then we can call it is a very good stable sensor. So we have to go for the stability study before launching it in the market. So thank you, everybody. These are the books. You may have books in your library. Thank you. Is there any question you may ask?
Yes, ma'am. Thank you. Audience, you are requested, if you have anybody any question, please ask.
Ma'am, myself, Dr. Anubruta Mandal. Ma'am, actually, previous 1 to 2 years ago, actually, I do some laboratory work in the LED in case of thermal conductivity, some experiment actually work through the graphene. Graphene is used basically in case of thermal conductivity in case of LED. And that time we actually see these all types of properties and that you say in these sessions. And it is very much resourceful, ma'am, for our illumination engineer actually.
Okay, okay. So you have fabricated graphene at that time in your laboratory?
No, ma'am. Actually, my area is actually design purpose, only
Okay.
lighting design. But
Okay.
some research scholar and me, just one thing is in case of thermal activity. Actually, we use console software.
Okay,
Is that
software based. Okay.
yes, 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 ma'am. Yes.
Mhm.
Thank
Who,
you, ma'am.
what is the
Thank
name? What is the name of?
my name is Onubroto Mondal.
Oh, no. Okay.
Actually, in illumination laboratory, we do that. My guide is Professor Dr. Kamalika Ghosh, ma'am.
Okay, okay. No. So you have all the method, do the simulation particularly.
Yes, 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 ma'am. Yes,
We have fabricated graphene in our laboratory.
yes, yes, yes,
That is the
yes,
thing.
yes.
So it is very tough to fabricate
Definitely, ma'am. It
because
is very
while
tough, very tough.
very tough because when you are getting the graphene, this is floated onto the solution. So it is
Yes,
very
yes.
tough to take the graphene from the solution and put it on the silicon substrate because it will break.
Break. Yes, yes, yes. And
Very
this is
tough.
very, very thin, actually.
Very thin. You can
Very thin.
see the graphene layer when it is floating in a water.
Yes, ma'am.
Okay.
Okay,
But
ma'am.
the exchange
It is.
solution is that. Okay, please.
Yes, and yeah, actually, this presentation is very, very resourceful for our in case of illumination engineer, ma'am. If possible, please share at least graphene portions, is if possible. You share
Okay,
actually.
okay,
Yes,
sure.
yes, 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 ma'am. Ma'am, thank you very much, ma'am. Over
Thank
to
you
you,
to all of
Rajashri,
you.
sir. Yes.
Yes, sir. Thank you, ma'am. Very much informative and insightful presentation as always. It is nothing to say because we know sir, madam very well from very beginning, from very previously. So ma'am is always helping and very much insightful presentation as always. We are always seen in previous any presentation part also. So this is as per Onubroto sir also, it will be very much helpful for any research scholar and very much resourceful presentation as because that's why it will be very much helpful for others also. So we would like to thank our speaker ma'am, Sunipa madam, as well as our Onubroto sir also. And audience, if you have any query, please ask. And we would like to request our Onubroto sir for presenting the memento for a small token of appreciation for ma'am. This will be
Sure,
sent to
sir.
ma'am
Yes.
also. Yes, this will be sent or mailed to madam also. Madam, please accept.
Yes,
Onubroto is
thank you
presenting.
very much.
Yes, ma'am.
Yeah. Thank you very much.
Sir,
For
is it visible, sir?
yes, yes, absolutely.
Yes,
visible.
yes.
Okay, okay.
Madam, this is for you. Please accept digitally now.
Thank you.
And
I'm
we will mail very
accepting.
shortly. Yes,
Okay.
ma'am.
Thank you very much.
Thank you, ma'am.
Thank you to entire team. Okay. Okay.
Okay,
So
ma'am. Okay, ma'am.
Okay,
Thank
ma'am.
you.
Okay.
may I leave the session?
Okay. Yes, yes. Yes, ma'am. Yes.
Bye, everybody. If you have any query, you may contact me directly over mail.
Okay, ma'am. I share your mail ID. Actually, some participant had asked to your mail ID. I share your
Which
mail ID.
one, sir? Which one, sir?
Is this your official mail or personal mail, ma'am?
No. Official means which one? I mean
Uh,
head or
no, your
GNIT
personal official mail.
GNIT.ac.in, right?
Yes, 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 yes.
Yes, yes, that much. That
Yes,
I am
yes.
asking about. Okay. Thank you
Okay.
very much. Thank you to all the participants and organizing team and the principal madam of GKC.
Thank you, ma'am.
Bye. Hmm.
Participants are requested to don't leave the session. Actually, our next session will start from 4 p.m. Actually, our first
Yes.
session will not from the 10 a.m. Due to some problem of our speaker. So first sessions will held reschedule and that will start from 4 p.m. And I will share feedback link as well as assignment link in live sessions within 1 minute.